Okay, welcome back, everybody. In the previous lecture, we went over some basic physics associated with ECT. Specifically, we looked at old ECT machines that used to use a sine wave, and this is how electricity comes out of any wall socket as a constant flow of electrons, versus a square wave, which is what most ECT machines and practices utilize. And again, the rationale for using a square wave as opposed to a sine wave is that it helps to substantially cut down on the number of electrons passing through the brain, which helps to reduce the cognitive side effects, specifically the retrograde and anterograde amnesia that is all too often associated with ECT. Looking at some of these terms, we have first and foremost a coulomb. What's a coulomb? It's just a unit of electrical charge. 1 coulomb equals 6.241 times 10 to the 18 electrons. And when we want to calculate the charge, or again the dose that we're going to give to the patient, we do it by simply adding up all those boxes. So a frequency, and we're going to multiply it times 2 since it's a biphasic waveform, one above and one below the x-axis, times the total duration, 8 seconds. That tends to be the longest duration that most ECT machines can use, times the pulse width, and we have a range here, ultra brief, brief, and then regular pulse. And then times the amplitude. So how high is that box? And that is measured in amps or milliamps. And when you go through and do the calculation, 0.8 times 0.00037, that's again the pulse width, that's the amperage or the amplitude, times 120, which is the frequency, and again times 2 because it's biphasic, times 8, or the total duration, you get 568 millicoulombs, or 0.568 coulombs. And that again is the dose. Taking a step further, what about energy? That's measured in joules. That is simply the current, or the amperage, squared, times the resistance times time. So think of the time variable as the total duration of boxes. You're just adding all of them up. So many boxes per second with such and such a pulse width, measured in milliseconds, times the total duration of stimulation. And continuing with the example above, if you have 0.8 amps, again squared, times 220 ohms, times 0.00037 seconds, times 240, that's again the 120 times 2 because it's biphasic, times 8, which is the duration, you get 100.02 joules. So maxed out, going to be approximately 100 joules. Taking it one step further, a long time ago a medical student asked me about voltage. And I thought that was kind of a silly question because it's not really relevant. It never came up in any of my training. But still, to help you understand the physics of what's happening, it was kind of fun. And so a couple years later, now I can give people an answer. Voltage, just using this formula, is just simply just energy divided by the charge. So 100.02 joules divided by 568 coulombs is going to be approximately 176 volts. And as we decrease the charge, as that goes down, the energy is also going to go down. So it'll be approximately 175, 176 volts, whatever setting you are at. And think of voltage as simply the difference in gradient of how hard do you have to work to push those electrons through the brain. So the lower the resistance, the less voltage needing to get that same charge through.